Hi folks, we're going to take a look at number 17 from page 570. So they're telling us that the cross-section of a water trough is an equilateral triangle. Okay, so we'll talk about the shape in a second, but let's see, they give us some information. They tell us that it's 5 meters long, 25 centimeters deep, and it's telling us that water is flowing into the trough at a rate of 0.25 meters cubed per minute. Okay, so essentially what they're telling us is that the volume of water inside the trough is increasing at a rate of 0.25 meters cubed per minute. So that means they're giving us the derivative volume with respect to time. And we know it's positive because the water is flowing in. And they want us to know how fast the water level is rising when the water is 10 centimeters deep. Okay, so looks like we're looking for the rate of change of the height of water inside the trough. Okay, so first thing we have to figure out is what shape are we talking about? So if not sure what a trough is, normally we think of it as something pigs eat out of, all right, and it takes the shape of a prism, and in this case here, a triangular prism. Okay, so let's try to draw it here. So if you didn't know what a trough was, best thing to do would have been to look it up and get a sense of what the shape should be. Okay, so the base of this trough is going to be an equilateral triangle. Now, presumably that'll be of some use to us if they're specifically telling us that it's equilateral. And then, of course, there's the length of the trough. Okay, so there we go. So we're working with a shape that looks like this. Okay, and water is flowing in. So as water pours in, okay, we realize that the shape that the water is going to take is just going to be itself a smaller triangular prism. Okay, so obviously the base is going to be smaller, but it's still going to have this length of 5 meters. Okay, and they tell us that the depth here is, okay, now they tell us it's 25 centimeters, and that's when I realized, oh, wait a minute, I've got different units here. I got to decide what I'm going to be working with. But I think it's easier to turn 25 centimeters into meters than to turn 0.25 meters cubed into centimeters cubed. So what I'm going to do is I'm going to turn 25 centimeters into 0.25 meters and just do the whole problem that way. All right. So what we want to know is how fast the water level is rising. All right, and what we know is the rate of change of the volume. So what we're going to need is an equation that gives me the volume of water inside the trough. But since this is a prism, we know it's just going to be the area of the base times this length of 5 meters. Okay, and so since I'm looking for the area of a triangle, it's going to be base times height. Okay, so let me call the height of this triangle h. And this is also the variable I'm interested in, okay, because that's going to represent the increase in water level, okay, times the base of this triangle. Now, this is where I'm going to do something to maybe make my life a little simpler, because this looks a lot like a problem we've solved before. It looks a lot like the problem with water coming in or out of a cone, and we ended up using similar triangles here. So I have a sense that we might be doing the same thing. So what I'd like to work with is this triangle here and compare it to this larger right angle triangle. So instead of calling this whole thing x, I'm going to call just this portion x. And so the base of this triangle is just going to be 2x. Okay, so now I can write the function I'm going to use that'll eventually lead to my related rates equation. So the volume of this water inside the trough is going to be 1/2 base times height. So 1/2 base, which is 2x, times height, which is h, times the length here of 5. So I'm going to just be left with, these 2's cancel out, 5xh. All right. And as usual, I've got a function of 2 variables. So step number 1 is to eliminate one of these variables, and presumably I want to eliminate the x. Since the h is the one that I'm actually interested in, I'm hoping to substitute the x from this equation. Okay, and this is where now I'm going to maybe draw a bigger version of that triangle so I can work with it a little. Okay. So this total height is 0.25. The height of the water level, we said we were going to call H. We'll call this side here X. And this is where I realize I have a bit of a problem, as I don't know the length of either the top of this triangle or even part of it. Okay, so I can't set up a proportion yet to hopefully relate X and H. Okay, but this is where I remember that thing they told me about the triangle. They told me that it was an equilateral triangle, and I know that all three angles in an equilateral triangle, like the sides, are going to be the same. Okay, so all three angles are just equal to pi over 3, or 60 degrees. Okay, so all I have to do now is, well, I'm going to use a little trigonometry. So here I've got, I'll call this y up here, and I realize I can use tangent. Okay, I have that tan of pi over 3 is equal to the opposite side, which is this 0.25, okay, over this adjacent side, which is y. So y is just going to be equal to 0.25 over tan of pi over 3. Okay, now since this is an application question, I'm just going to approximate here. So let's do that. We've got 0.25, and let's check. I am in radians, so 0.25 divided by tan of pi over 3, and that's equal to 0.144. Okay, I'll keep an extra decimal place there along the way. Okay, so this is 0.144. So now I can set up a proportion with my similar triangles. So I have X over its corresponding side of 0.144 is going to be equal to H over its corresponding side, which is going to be this whole length here, which is just 0.25. Okay, and as we said, we're going to isolate X and substitute into our equation because I want H to be the one that remains. So X is going to be equal to, so I'll just bring this over to the other side. I just have to do 0.144 divided by 0.25. So I already have that in the calculator, divided by 0.25, and that's 0.577. So 0.577 H. Okay, and now I can finally input all that into my equation. So I have 5 times X we just found was 0.577 H times the H that was already there. And so what do we have? We have volume is given by, and let's calculate that, 0.577 times 5 is equal to 2.887. Okay, 2.887 H squared. And now I can finally take the derivative with respect to t of both sides. So we have dv dt equals, so 2.887 is just a constant, and the derivative of h squared with respect to t, remember with respect to t, is 2h dh dt. And now I have enough information to find dh dt, okay? Because I know the derivative of volume with respect to time, it's 0.25 divided by 2.887 times 2 times the height at the particular moment I'm interested in, and the height at the particular moment I'm interested in is 10 centimeters. But remember, we're putting everything in meters, so that's just going to be 0.1. And now we can calculate this to get our final answer. So we have 0.25 divided by 2.887 times 2 times 0.1, and that gives us 0.433. Okay, 0.433, and remember that our units are in meters and time in minutes. Okay, and there we have it. So this problem here was a little more interesting than most of the ones we've solved, because normally they would have given us enough information to set up our proportion for similar triangles. Okay, here we just had to do some of the work ourselves, and it came down to knowing that this was an equilateral triangle. Hence, we knew one of the angles in the triangle. Okay, so just to recap, step number 1 is, again, make sure you understand your diagram. So if you didn't know what a trough was, you should have looked it up. Okay. And then hopefully recognize that this looks a lot like a problem we solved where similar triangles came into play. So once you have your function in one variable, you can then take the derivative of both sides to create your related rates equation and then use the information given to find your answer. Okay, that's it for this one.